All right, everybody, here we go. 2.2, energy and biomass in ecosystems. No need to copy this, but I'm going to start highlighting each section in pink. It's going to make it easier for me to find on the notes, probably you to find as well. So, yep, there we go. Hopefully this goes quick because I've got people showing up for trick or treat hopefully in a little bit. So we got to be handing out some candy here. Energy and systems. Energy is held by the laws of thermodynamics. So define the first of all the first law of thermodynamics. It's the principle of conservation of energy, page 129, something like that. And you can probably find it like this. Let's go first law of thermodynamics. Pow. All right. Yep. Probably any of these definitions would probably be good. There's Wikipedia for you. Okay. Ooh, there's NASA. A little bit more legit. All right. Good. All right. Define total energy of the universe is constant. We don't make energy. We don't destroy energy. Energy just transfers and transforms. So yeah, you don't really make energy. So energy's form can change, but is not created or destroyed. Just like I just said. Explain an example that transforms energy. Okay. What is a heat pump? How is it more efficient than burning oil, gas, or wood for heat? Keyword in there, burning. So, yep. Got to create heat with that one, where that one it just transfers. So, yeah. So, yep, transfers versus transformation. Respiration, photosynthesis, page 130 to 131. Got to define them. Cellular respiration, yep, going to keep going on with that. Entropy. Ooh, entropy is craziness. So, yep. Photosynthesis. Yeah, you should know that if you took biology. Second law of thermodynamics. Good. Well, I'll give you a little breather here. See here. Second. Get rid of that T. Law of thermodynamics. Sweet. Let's see what it says here. A little bit more explained. Okay. Is a physical law based on universal empirical observations concerning heat and energy conversion. So those laws that heat always flows spontaneously from hotter to colder regions of matter. All right, downhill. So yep. Respiration, basically the breakdown of stored energy for use and waste. It's what you kind of do for living, just like just you live in your everyday life. A plant live in its everyday life. It's energy used for living. That's what respiration is. Plants, animals, bacteria, fungi all respire. So, yep. Failure to respire means life has ceased. You come down with a bad case of dead. It's terminal. Sorry, not going to improve. So, yep, if you're not respiring, you're decomposing probably. Happens during every moment of life, regardless of sunlight or sleep. Yep. So, yep. Living processes fueled by respiration can be movement. All right. Respiration. Sensitivity, just using your senses. Growth. All right. Reproduction. You can figure that one out on your own. Excretion. That's pooping or pissing. Yep. Nutrition. Eating. Drinking. Cider, a little bit of maple syrup in there too, and some nutmeg. Just give it a little spice. All right, it's fall time. Aerobic respiration with oxygen. So aerobic is where like you're able to breathe while doing it, like a long distance run, bike ride, long distance. All right. Anaerobic is where you're just sprinting. All right, or powerlifting. Energy is released and used during aerobic respiration. Products are carbon dioxide, water, and energy. So yeah, you're putting out energy in the form of heat. You're putting out water in the forms of like moisture in your breath. All right, also carbon dioxide there. So most energy that you put out is heat. Heat is released from the cell to the body, and then from the body off to the atmosphere or environment. Once in the environment, it's gone forever. Body can't use it. Nature can't really use it either. It's Dunsky. Yep, not gonna get it back. What is your favorite sport event? Relate doing your sport to heat production. Yeah, think about what you're doing. Even if you're in a pool, guess what? If you're moving, your body's producing heat. So, aerobic respiration without oxygen, pumping iron, sprinting. Okay. Photosynthesis, transformation energy from one type to a different type. Leaves have chloroplast. Chloroplasts are green with chlorophyll. Chlorophyll is basically where the photosynthesis happens. So, yep. Chloroplasts use sunlight to split water, combine it with carbon dioxide to make glucose. Glucose is used by the plant to make all other cells. So glucose is basically the building block. Yep, and the plant makes it itself with sunlight. Without sunlight, no worko. So nitrogen plus sulfur to make amino acids, then proteins. So proteins are the building blocks that you're always told about. Some of those amino acids, us as humans, our body makes. Some we have to get from outside sources. So we rearrange the carbon, the hydrogen, the oxygen. We don't make them, we just rearrange them. Plus phosphorus, and we use it to basically make up your fatty acids and your proteins, lipoproteins. Remember doing the maple syrup project? Which leaf is a cow more likely to eat, a sugar or red maple? And why do you think that? Interesting, right? Jeopardy question. All right, let me put that question right up there for you. Yeah. All right. Photosynthesis makes biomass. Animals directly or indirectly depend on plants. If you're a primary consumer, you eat plants. If you're a secondary consumer, you eat the animals that eat the grass. So, just the way it is. Most human nutrition comes from eating. Yeah. So humans can make 11 of the 12 amino acids. Remember I was talking about that? We make most of them ourselves. And the problem is those other 9 are essential amino acids. They're the ones you can't make. You just got to consume via nutrition. So photosynthesis waste is oxygen, a very useful waste product. We as humans kind of like that waste product because that's what we breathe in. So yeah, this is why trees are important. Trees take in carbon dioxide, which we produce a lot of, as just humans. And then, get big on it. Breathe out oxygen. So plants, very useful for that. Let's see. Useful waste product. Yep. Define compensation point. Early morning and evening compensation point happens. Plant is maintaining, neither consuming or building. Not going to lie to you, just in the past, I haven't seen a whole lot on compensation point in IB exams. So, for what it's worth. Second law of thermodynamics, quality of energy. Is it clean or is it not? All right. As transfers of energy happen, a lot is lost to heat energy. Inefficiency. Because when you're losing out in heat, it's not as efficient. Gas car, chemical reaction, produces energy. Well, produces mechanical energy. It also, though, produces heat. Electrical motors do not produce heat. So do not lose any in heat, which is why they're more efficient. Efficiency equals useful energy produced, the amount of energy consumed times 100. Yep. Food chains and trophic levels. Almost all energy comes from the sun. Yes, all right. Pretty much all energy comes from the sun. So, TOK, all energy in the universe will eventually become heat energy and no more energy transfers will happen. Equals thermal death of the universe. This is a rather dark matter, but to what extent is imagination crucial in the creation of this hypothesis? Yep, dig down and deep for me with that one. So basically what it is at the end of the universe, when we're all done, probably your grandchildren's grandchildren too, there's no more, sun's died out, no more energy coming from it. All the energy we've consumed, basically we put out as heat, and then the heat is useless to us. So define page 132, consumer, trophic level, producer. Yeah, actually you probably hit these up a little bit on test 1, to be honest with you. So, but still hit them up, give me some definitions. Food chain shows. Ooh, okay. Feeding relationships between species. Yep. Who is eating plants? Who's eating animals? And who's eating animals that eat animals? Yeah. Energy transfers. Arrows point to the consumer plus flow of energy biomass. Trophic level is the feeding level, usually horizontal. So this would be a trophic level right here. Actually, that's kind of interesting. Those are some, yeah, right? Huh. Yeah. Yeah, these are kind of apex predators here, I think. It's interesting. It's just off size. Yeah. All right. So let's take a look here. Primary producers, primary consumers, right there. Yep, right there. Good. Now over here, you're going to have secondary consumers. Yep. And then tertiary consumers. Yep. Decomposers. So, with reference to figure 5, state the trophic level of the red-crowned crane. Let's see. I'm going to say tertiary consumer. Yep. Primary producer, primary consumer, secondary consumer, tertiary consumer. Yep. Outline the potential impact of the food web shown in figure 5 if the Hokkaido salamander becomes extinct. So if this guy, if they all get just, I was thinking of an English word, but I probably shouldn't say it. I don't know what it means. So if they all just die out, what's going to happen? All right. So this guy right here, that's all he eats is those Hokkaido salamanders. So that red crane is going to die. Yep. Let's see. The Hokkaido owl will still be living. And the least weevil will still be living as well. In fact, their numbers might grow a little bit. Yeah, no, it wouldn't impact the other numbers. But their numbers would decrease a little bit. Less food. So, yep. All right. Food webs. Most animals eat a multiple of things. Actually, let's get that one there. Most animals eat a multiple of things. So food chains are complicated. Animals can also eat more than one trophic level, complicating things further. Think about us as humans. We're vegetarians. We have some of us that are primary consumers. All we eat is vegetables. Then you got other ones of us that most of us are secondary consumers because we love us a hamburger. Yep. And then you got tertiary consumers, which they're the ones who eat meat from animals that eat other animals. Think of someone that eats bluefish or bear meat. I'm just thinking of ones that we've eaten before that eat animals. So yeah, it's kind of gamey. Not the meat. The taste isn't as good. Yep. So first food web was done by Charles Elton and Alistair Hardy in 1920s. And yeah, it was pretty in-depth and pretty complicated. Most animals will alter their diet to eat what's available. They're only as faithful as their options, So you will eat just about whatever it takes to survive. Efficiency of energy transfers. Number of trophic levels limited by energy transfers. Eventually, energy runs out. Yep. So majority of energy is lost as heat. That's why trophic levels on land usually go for 4 places. In aquatic systems like the ocean, they can go for 5. But you can't keep going up levels because 10%, 10%, 10% at each level, eventually there's just very little energy left. So most of it's lost as heat. Heat can't be used by higher trophic levels. So think of it like this way, whether you're a vegetarian, that grass, the lettuce you eat produced heat. Can you harness it at all? No. All right. Hey, that cow produced heat. If you're eating hamburgers, can you eat the heat? No. All right. And no, hot sauce doesn't count. So, yep. Not as efficient as us. Let's see. On average, 10% of energy is transferred between trophic levels. That's on average. Smaller animals are not as efficient as bigger animals. Bigger animals tend to be at the top of the food chain or food web. Smaller animals tend to be at the bottom. There are exceptions to the rule. Elephants are vegetarians. They're pretty big. So, smaller animals, not as efficient. Herbivores, not as efficient as carnivores. Yep. If you're eating grass or veggies, you got to eat a lot of it because it's not as easily digestible as meat, you could say. Like, it's just not as we don't get as much energy from it. So you got to eat more of it. Cold-blooded animals are more efficient than warm-blooded animals. Yep. Trophic inefficiencies happen because not everything eaten. So yeah, you eat hamburgers again, right? Do you eat the cow hooves? Do you eat the horns? Do you eat the hide or the hair? Not really, right? So yep, not everything's eaten. Inefficient digestion. When you eat a hamburger, it goes into your intestines. The intestines are what absorb the matter or energy. And your intestines can only absorb so much in certain types. It's inefficient. That's why a lot of it comes out as poop or fecal matter. So, yeah. Now that heat is lost. So, yeah, you absorb all those nutrients. Congratulations. Just by you respiring, just breathing, living your life, you're producing heat, which is lost. Energy used in reproduction and life processes. You're not getting that back. So, yep. So that's why there's trophic inefficiencies. The efficiency percent equals the biomass of higher trophic levels divided by the biomass of the lower trophic level times 100. So that might actually be useful for an IA. Like any of these equations you see here. Just wondering here. Maximum sustainable yield, MSY, used a lot by IB. At least it used to be. I'm not sure with this new exam. All right. It's great for measuring like farmland and how much crop you can plant and how much profit you can get from the land. Assumes species population naturally produces more than necessary to replace losses. So with humanity in the United States, this would not be the key because our birth rate is lower than the death rate. For every 2 people that die, we've got like one. Let's take a look here. Birth rate USA. All right. Yeah, let's see. That's not really showing me what I wanted. Yeah. All right. Whatever. Assumes. All right. Surplus can be harvested by humans. So it's a good thing we got off of that talk about humanity. So yeah, if 2 ears of corn produce 4 ears of corn, then we can reap 2 ears of corn and the number will stay the same. MSY, maximum sustainable yield, net productivity of species or trophic level that can be harvested without reducing future supply. So yeah, that's why it's sustainable. Applied to a lot to fishing limits. So yeah, how many fish are being produced of that species? How many can you take in? So measuring of biomass, collect and dry samples, then weigh it. So definitions on page 137. Productivity, gross productivity, net productivity. Productivity, define those for me. So productivity, when you start looking at GPP, gross primary productivity, plants. Because remember, we're talking about primary producers, not consumers. GSP, this is the gross secondary productivity. This is your consumers. So this is your primary consumer, this is your secondary consumer, all the way up the chain. Net productivity is the energy taken in, energy lost, and all organisms use energy to just stay alive. Respiration, remember we talked about in the beginning? Yep, everybody respires unless you're dead. In that case, don't worry about that. Ecological pyramids, right here. Quantitative models include numbers, biomass, and productivity. Measure over specific time for specific areas. Easy to see energy transfers plus losses. Show species at trophic levels. Show what feeds on what. show ecosystem balance. Let's take a look at that. Ecological pyramids. Ecological pyramid. All right, pow. Images. Yep. Good. Oh man, my face is in the way. Yeah, that one looks pretty cool right there. Shows some numbers right there. Good. All right. Doesn't matter numbers as much. All right. Pyramid of numbers shows the number of organisms at each trophic level at one moment. Again, it's a snapshot. So measured in numbers unit area. Longer the bar equals more organisms. So most pyramids have broad bases and a narrow tip. You're gonna have less lions than you do gazelles in wildebeest. Let's see. Advantages: it's simple, plus shows the population numbers changing over time. Disadvantages: it doesn't take organism size into account. It's not going to show you how big a wildebeest is. Doesn't show the organism's age, if it's young, small, old, whatever. All right, numbers can be too big for accuracy as well. Let's see if we can get you a pyramid of numbers. Pyramid of numbers. Yeah, I like that. These ones would be it right here. All right, let's get this one there. All right, so you're gonna have more plants, and you're gonna have more mice, and you're gonna have more snakes, and you're gonna have more eagles eating the snakes. Yep, just like that. Awesome. So pyramid of numbers done. Pyramids of biomass. Biomass of each trophic level. Biomass is the mass of each individual times the number of individuals. So if your average student in 11th grade weighs, let's go with 140 pounds, times in our class, like if you're a junior class, you probably got 80 people. So 140 pounds times 80. Yep. Basically the dried organic material of what you've measured. So most look like pyramids, but oceanic can look different. Advantages: it gives more info than period of numbers. Disadvantages: organisms must be killed, which means they are not. You can't use this one for IAs to measure the biomass, which IB doesn't allow. No, definitely a way to fail. Only samples the larger population, so it's impossible it will be perfect. Time of the year measures effects results as well. So if you measure just with migration or birth cycle, stuff like that. Animal biomass is different. Tiger and bear weigh the same, but different muscle fat proportions. Bears are some chunky, fatty animals come fall time. So species have different amounts of non-digestible parts. Again, it's just a snapshot in time. What they mean by this is this. Some animals just have more bones and hair and hide than others. So, yep, for that one right there. So we'll take a look at pyramid of biomass. Here you go. Upright pyramid right here. Yep. Let's see. Yep. Lovely. Good. All right. Pyramids of energy shows the rate of energy flow, biomass between trophic levels. Show flow over time, so are not snapshots. They follow the second law of thermodynamics. They're always pyramid shaped. So productivity values are the rates of energy flow. Biomass values are the stores of energy at a moment. Again, just a snapshot. Advantages: shows the energy flow over time. Allows comparison of ecosystems. You can compare jungle to a tundra. Can show sun energy input. Very useful. There's no inverted pyramids. All right. Inverted pyramid is where the pyramid goes down like that. Um, Disadvantages. Have to measure growth plus reproduction over time. Still have consumers at multiple trophic levels. Difficult to place decomposers and detrivores. So where do you put your fungi? Where do you put um, your your vultures, those scavenger eaters? Also, to humans and like other animals that you eat at multiple trophic levels, very hard to put. So, yep. Pyramids of energy. Let's see if we can get you a picture of that. Pyramids of. I think I saw one there, but oh dang it. Energy. Good. I like that one. Except my face is in the way. Yep. Ooh, right there. You see how we got the numbers? It's like 10%. Rainforest leaves. Yay! 100%. Now you got lost 90% of it because it just do it with the trophic levels. Now you're down to 1%. Up here, crocodile. By the time that energy gets up there, you're basically 0.1% of the energy that was down here. So yeah, kind of just the way it works. All right, let's go over here. Let's move me over there. Good. So definitions. Give me biocides, bioaccumulation, biomagnification. IB loves these so much so that you probably should have used them when we were talking about chapter 1 test. So, yep. Even though we're giving to you now, you probably already had to use them. So, consequences of pyramids and ecosystem function. You are what you eat. Pesticides equal chemical designed to kill, limit, or repel pest. Biocides can be consumed and transmitted up the food chain. Plants can take up poison, pass it along. Bioaccumulation occurs. So basically what you talk about is like, okay, poisons can get into plants. Now, there's more plants than there are primary consumers. So how many blades of grass does that cow eat in its lifetime? Then how many cows do you eat in your lifetime? So you can see it just starts going accumulating. Very good. Because the life of higher trophic level organisms is generally longer. Yeah, humans live longer than cows. There's more time for biomagnification. So cows will eat grass its entire life, 30 years, whatever it is. All right, you will eat cows your entire life, 80 years. So this can cause death, limit reproduction, bald eagles, and negatively impact abilities. So how many blades of grass does the cow eat? How many cows do you eat in your lifetime? I love cheeseburgers. How much does that grass toxin magnify in you? Some decompose, but others, like POPs, persistent organic pollutants, which was on a test question for test 1, and forever chemicals don't break down. So they're around forever. That's why they're called forever chemicals. Humans' impact on flows of energy and transfers of matter. Every action has an equal and opposite reaction. So everything we do impacts the environment, good or bad. You walk into school, you have an impact on the environment. Sorry. You're riding a school bus. Yep, has an impact on the environment. Everything we do impacts another. That's the way just the energy flows in the environment is. The environments aren't static. Ecology is not static. It is dynamic. It is constantly moving and changing and adapting. Define page 143 and 144. Pesticides, heterotrophs, autotrophs, primary productivity, gross primary productivity. Sorry about that, GPP. IB loves them some GPP. Net primary productivity. IB loves them some NPP. So more on energy sources coming right up. So you got right here. Let me bring that down just so you can get a vibe with that. So Photoautotrophs, they're photosynthetic bacteria that use light energy. Look, they're not common. They're definitely a specialty in biology if you're going to study them. Um, we're not going to get into them too much. So, chemotrophs, organisms that use chemical energy, bacteria that live deep in the ocean vents. Nitrosomonas and nitrobacter are two bacteria in the nitrogen cycle. So, yeah, just put those on the shelves for a little bit. Know about them, but we're going to focus on some other things for right now. More on productivity. So, gross primary productivity is plants gain in energy or biomass in an area over time. So, what's left over after photosynthesis and respiration? What's left over after you make energy and then you lose energy just from living your best life? That's what's left over for growth, the gross primary productivity. Hard to measure this though. Why? Because most of the time you got to kill, chop, dry, and all that sort of stuff. Net primary productivity, NPP. GPP minus respiration. So basically, how much the plant's grown. More real world and useful than GPP. Ecosystems NPP is the rate of plants put on dry mass. How quick does those trees go in the sunlight? Some for life processes, some for putting on mass. Biomes have different NPP rates. So rainforest has a high rate, the tundra has a low, just like anything you'd expect in the tundra. Time of the year affects the NPP as well. So rainforest, you grow year round. There's no real off season that I know about. Up here where we live in Connecticut, the trees are pretty much dormant during the winter. So, yep. And page 145 and 146, please define the next few words. Secondary productivity, gross secondary productivity, net secondary productivity, ecological efficiency. So, move my face again over here. Yeah, good. Net secondary productivity, NSP. Not all energy is consumed, is available. A lot of energy is lost. Assimilated food energy, energy that's transferred across the intestinal wall of animals. Remember when I said very like you consume a lot of energy and your body's like, we can only take in so much through the intestines. You got to just send the rest of it right out the other hole other than your mouth. So if the energy doesn't cross, it's lost energy, comes out as poop. Some goes for life processes, respiration, some excreted as pee, some grows NPP. So, yep, net primary productivity. Think of NSP as the next level of NPP. So NPP is primary producers, NSP is primary consumers. So let's see where we're at. NSP. Where was that? Yep. Gross secondary productivity is basically all the food that enters the mouth, including poop that leaves. So think of GSP as the next level of GPP. NSP is the food intake minus the poop out and minus the energy used in respiration. Very little of the original plant energy makes its way to the herbivore for growth. Even less when you think about sunlight, but we'll get into that. This pattern of energy loss as it travels up the food chain continues as you go up levels. Every level you go up, there's energy loss. There's an increase in entropy. Secondary consumers, carnivores that eat herbivores. Tertiary consumers, carnivores that eat other carnivores. That meat is usually pretty gamey, which is why we tend to stay away from it as humans. Herbivores absorb 40% of the energy they intake and poop out 60%. Carnivores absorb 80% of the energy they intake and poop out 20%. All right. Much higher than herbivores. I was going to get into something, but I'll hold off. It's why herbivores eat and lions sleep all day. So lions only spend a little time eating. The rest of the time just sleeping. All right, they only spend a little time hunting, a little time eating. Why? Because when they eat that meal, they absorb so much of it. Where you get those poor elephants, those poor zebras, the poor horses, they do not absorb hardly anything. So like they're the whole day they don't have time for a nap. They just got to keep eating, otherwise they'll just get skinny and die. So protein is more easily digested than plant matter. What poops more, a lion or a horse? We just talked about this. If you look at these numbers right here, they'll tell you. Maximum sustainable yield, NPP or NSP of a system. The largest amount that can be removed from the system and still be sustainable. Numbers are higher, lower in the food chain. So that means you can take out quite a bit more when it's lower in the food chain than it is higher. Look at a swordfish. A swordfish takes years to develop. When you take out a swordfish, one's not replacing it anytime soon. It takes years. You take out a sardine, man, it's replaced tomorrow practically. So you can take out as many little fish, sardines as you want. Yep. Swordfish, when you take one out, it impacts a lot more. Let's see. That's me. Well, it can be borrowed. What the heck was I? Sorry, peeps. I got off on a tangent. Numbers are higher, lower in the food chain. Eating meat higher up in the food chain supports wasting a lot of energy, mostly from heat. But meat gives more energy, so we do have to give you that. Vegetarians, they got to be eating pretty much all day. Eating vegetarian or lower on the food chain is more sustainable for humans when you're looking at the planet, because less energy is lost as you go up the ladder, up the food chain. Have you ever eaten an animal that is a predator? What did it taste like? Anyone ever eaten bluefish? Here in New England, there's bluefish in Long Island Sound and whatnot. My stepfather used to go fishing for them. Nastiest tasting stuff. Mr. Lewis, the RIT guy at school, would go fishing for bluefish. He ain't eating it. All right. Different ways people say, they're like, oh, you've got to smoke the bluefish. Oh, you got to put it in mayonnaise. It doesn't matter. It still tastes nasty to me. Some people love it, though. My dog loved it when we gave it to him. So, yep. Ecological efficiency. I need to know two things. Percent of NPP from one level is consumed by the next level. The percent consumed material turned into new tissue and percent used in respiration. So, yep, those are the two things you got to know for it. Animals raised for meat. How much of the grass it eats is assimilated? How much is not? It's just you're pooping right out. Efficiency of assimilation equals the gross productivity divided by the food eaten times 100. So now we're not bringing that up for IAs. That could get really messy and disgusting. How many animals can be in an area, though? That's why it's useful right here. That's why farmers tend to look at quite a bit. How many animals can they put on their land? How much will they profit from it? How much of assimilated energy is turned into meat? Efficiency of biomass, productivity, net productivity, gross productivity, times 100. This is used for profit, by the way. How much is assimilated energy is turned into meat. The length of food chains. General rule, only 10% of the energy is transferred from one trophic level to the next. Yep, good rule to go by. Most energy lost in respiration plus heat. The second law of thermodynamics really comes in here, just about clean energy. Even more is lost because animals stomp on plants to get food. If you've ever gone blueberry picking or, like wild blueberry picking, you're going to be stomping on some bushes and to get those blueberries. The result is that there's quite a bit lost just by us stomping on it. Think about apple harvesting. How many apples do you see on the ground? So don't get me wrong. I mean, the deer come in at night and eat them. The insects eat them. You can use those apples too to make cider. All right. But generally there's quite a bit of waste. So Little energy is left after 4 land trophic levels or 5 ocean trophic levels. Why top carnivores are in trouble. Takes a lot of energy to make big apex predators, so there aren't a lot of them. You don't see lions roaming around too often. Here in New England, what apex predator do we have? Bears, maybe, but even them, all the black bears that were scared that it would attack humans, they got hunted out a long time ago. So hard for them to grow big. It really is. It's just, find a small island, name it, and find out what the biggest carnivore is on that island. Yeah. Go for Puerto Rico. Go for Jamaica. Go for Hawaii. Go for Trinidad. Go for Tobago. Go for Ireland. All right. Go for England. Often higher on the food chain is more sustainable. More susceptible. Sorry, I knew something didn't equate there when I read that off. Bioaccumulation and biomagnification. All those toxins in the lower food chain go right up top. And if you're living longer up top, that means you're accumulating more and more of them. They get magnified. So predators tend to have a more limited diet, so changes hit hard. Think about this. You're eating plants, you'll eat a ton of different plants. Well, guess what? If you're eating meat, you have less selection at the dining room table. So predators have a lower resilience. It takes quite a bit for us to bounce back. So, versus plant, which is if you're an herbivore, primary consumer, you bounce back rather quick. So, which is all right. Anyway, more on entropy. Entropy is the measure of the amount of disorder. Increases over time. More entropy equals less order. So more craziness. Because energy transformations are never 100% efficient, it's just the way it is. The further up the chain you go, you're going to get more craziness, more entropy. Work produces waste heat. And again, you cannot harness that waste heat. It's useless. Plants convert sunlight into sugars, photosynthesis, at 1 to 2% efficiency. Wow, right? We're going to come to that in a question, so just remember it. Primary consumers turn 10% of energy into new tissue. So the secondary consumer's efficiency is 10%. Energy lost as heat to the environment obviously cannot be used and is useless. Useless. Most solar panels' efficiency is 20%. That sounds pretty low to me. It doesn't, you're thinking, well, put up a solar panel, it only gets 20% of the sunlight's energy? Say, what? All right, looking at your notes above, though, is this more or less than plants? Oh, it's more. It's about 18% more. So, simple examples of entropy. Draw a tidy room and label it low entropy. Then draw a cluttered, messy room and label it high entropy. So, just a good way to remember that. Let's take a look here. I don't think we're getting into this one. Yeah. No, we're not. All right, everybody, that's the video. Hope you enjoy.